Hello, today I'm going to talk about aerodynamics. So we learn about different components of the aerial system, and specifically we are focusing on the fixed wing unmanned aerial system. So today I'm going to talk about aerodynamics and how we can run different types of analysis on different parts and give you an introduction of the aerodynamics. And once you get to the software XFLR5, so we know that what are the results that we are getting or what type of analysis we are doing. So there are three different terminologies, including the aerodynamics, gas dynamics, and the hydrodynamics. So aerodynamics, once you have flow of air, for gas dynamic, we have flow of gases, and for hydrodynamics, we have flow of the liquids. So once you are dealing with an object which is moving in the air, we need to run aerodynamic analysis. If you have an object like submarines or some underwater robots, they are moving under the water, so we are dealing with the hydrodynamics. So once you are dealing with the rockets or missiles, so they are going actually to out of space and there is no any atmosphere, so we are dealing with the gas dynamics. So these are three examples that we can see here. So for example, this is an airplane which is moving in the air, or this is a car which is again moving in on the earth. So we just have the flow of the air. So therefore, we need to run different types of aerodynamic analysis to simulate the flow once they're passing through these vehicles. So this is an underwater airplane which is moving under the water. So here we are, our fluid is actually liquid water. So here we are dealing with the hydrodynamics. And this is a rocket. As you can see here, how the rockets works, we are dealing with the gas dynamics. So these are the three different terminologies that we have for any solid object which is moving actually in the different types of the flows. So aerodynamic is categorized as a continuum flow or low density and free molecule flow. So this is the way that we are actually dividing the types of the aerodynamics. So the continuum flow can be, for example, in the air that we have in our atmosphere, and for low density and a free molecule flow is, if I want to give you some example, for example, if you fly on Martian environment, on Mars atmosphere, the Martian atmosphere is very, very less dense. So it has a low density, and the molecules of the particles are actually free, and they have higher distances than the molecules that they are on Earth. So here we are dealing with the low dense atmosphere. So the aerodynamics in the continuum flow is going to be different with the aerodynamics in the low dense flow. So for continuum flow, you know, any type of the flow has a viscosity. Viscosity means that there is a friction for an object once is moving over, or inside of this flow. So depend on the value of the viscosity, we can have a viscous flow or we can have an inviscid flow. Viscous flow, it means that we are considering the shear stresses, we are considering the viscosity of the flow. But for inviscid flow, we are assuming that the viscosity is so low and negligible. So if I want to give you an example of the viscosity, if we compare, for example, oil and water. So if we have a slope, an object with a slope or a plate with a slope, and if you put water on this slope, or in the other side, if you put the oil, so we see that the water can move faster because of the less viscosity that the water had with our surface. And the oil, it's going with the lower velocity because it has a higher viscosity. So then after that, we can classify our aerodynamic based on incompressible flow and compressible flow. Incompressible flow, it means that the density of the flow is constant. It's not changing with the time, it's not changing with temperature, it's not changing with with the motion. So this is called incompressible flow. We also have the compressible flow, which means that the viscosity of the flow, the density of the flow is changing under the different circumstances. So for example, once the pressure is changing or once the temperature is changing, so here your density are changing. So therefore, there are two main factors which are important once you want to determine the type of aerodynamics. So the first one is viscosity, that our flow can be viscid or viscous, or the density, which our flow can be compressible or incompressible. So then after considering all of this, we have four different regimes of the flow. We have subsonic flow. It means that we are moving, our object is moving in the flow with a lower speed. We have transonic flow, we have supersonic flow, and we have the hypersonic flow. So it means that here our flow is moving with a higher speed in the hypersonic, followed by supersonic, transonic, and subsonic. So this is the reason that we have different types of aircraft, as we discussed earlier, that they can be classified as subsonic, transonic, supersonic, and hypersonic. So there are two main factors which determine the regime of the flow. So one of the factors is called Reynolds number. The another one is called Mach number. So that I'm going to talk about that in this lecture. So the Mach number, the definition of the Mach number, is defined as the speed of your vehicle, or it can be your rocket, can be your aircraft, can be your drone, or any object which is moving on the flow, divided by the speed of the sound. So the V is the speed of your vehicle and the C is the speed of the sound. So this is a Mach number. So if your Mach number is less than 0.8, it means that the velocity of your vehicle is less than the speed of the sound. So we are dealing with a subsonic flow. It means we are dealing with a low Reynolds or low speed flow. If your Mach number is between 0.8 to 1, we are dealing with a transonic flow. So you see that these are the shock waves that they are created here. These are the dashed line. They are called shock waves. So if we have our Mach number between 1 to 1.2, we are dealing with a transonic flow with the Mach infinity. So it means that the shape of your shock waves are different in this condition C with the condition here that we have in the part B. If your Mach number is more than 1.2, we are dealing with a supersonic flow. And if our Mach number is more than 5, it means that your airplanes are flying 5 times more than the speed of the sound. So we are dealing with a hypersonic flow, which usually happens in rockets or missiles. So these are the classification or categorization of the aerodynamic flow based on the Mach number. So there is another classification, which is called Reynolds number. If our Reynolds number is less than 500,000, so we are dealing with the laminar flow. If our Reynolds number is more than 500,000, we are dealing with the turbulent flow. So I'm going to write it here. What is the definition of the Reynolds number and how we do this calculation? So the Reynolds number is defined as is equal to rho, which is the density of the flow, V is the speed of your object, C is called the chord length or the characteristic length, divided by mu, which is the dynamic viscosity. So rho is the density of the air, V is the velocity of your flow or your object or relative velocity, C is the chord length, and the mu is the dynamic viscosity. So if Reynolds number is less than 5 times 10 to the power 5, we are dealing with a laminar flow. If this Reynolds number is more than 5 times 10 to power 5, we are dealing with a turbulent flow. So this is another classification that we will talk more details once we get to the software. So any objects that move actually in the air, it generates some discontinuity on the streamline. So these are the streamlines that you can see here. Once they reached here and they pass the airfoil, you will see that how the shape of the streamlines become different. And the main reason that the lift is generated, so imagine that this is your object which is exposed to the flow of the air, or your object or your flow is moving with the speed of v. So here, the streamlines, once reached to this point, it would be separated to two different streamlines. One is moving at the upper camber or upper surface. The another one is moving in the lower side. So once they move through the airfoil, we know that this length at the upper side is more than the length at the bottom side. So for example, if the length from here to here, if I call this distance x1, the distance from here to here in the bottom side is going to be x2. So as you can see here, once this streamline goes to this shape, they reach in the same time at the end, as we can see here. So here we can say that once the flow is actually divided to two parts, one part is going to upper side of your airport, the other one is going to the bottom side, they will reach here in the same time. It means that, as we can see here in this streamline shows in this animation. So here I can say that T1 is equal to T2. But we know that our x1 is more than x2, as we said that upper camber or upper surface of airfoil has a longer distance than the lower side. And here we know that T1 is equal to T2, the amount of the time that this streamlines needs to move from upper side or the lower side of our airfoil. So now if we divide x1 by t1 and x2 by t2, what we will get here? So we have x1 over t1, since the t1 is equal to t2, and x1 is more than x2, so x1 over t1 is more than x2 divided by t2. So distance by time, it gives us velocity. So here we can say that velocity of the flow at the upper side of this airfoil is more than velocity at the bottom side. So the V1 is going to be more than V2. It means that the speed of the flow at the upper side of an airfoil is more than the speed of the flow at the bottom side of our airfoil. So there is a Bernoulli equation which shows that once the velocity of the flow in the one side is more, so the pressure is less. So once the V1 is more than V2, so if I write here, this is our V1, and these are the flow speed of V2. V1 is more than V2, so here, what we have here, the P1, which is the pressure, should be less than P2. So this is P1 here, and here is P2. So as you see here, pressure underneath is more than pressure in the upper side of my airfoil. So because of this pressure difference, so P2 is more than P1, so it will generate a lift force. So this is the source of generating the force. I will discuss this more once we get to software. This is just for your information to know how this works. So now, if I go back to that slide again, here, if I play this video, you will see that increasing the angle of attack. So here, if I draw a line, if I connect the leading edge to trailing edge, this is a horizontal line. It means that our airfoil doesn't have any angle of attack. So once the angle of attack is increasing, so the flow would be changed to the turbulent flow. As you can see here, this airfoil has an angle of attack, and this is a flow visualization. that we will see here. And now if we play this, see that how with changing the angle of attack of this object is increasing and how the flow is going to be turbulent. So you'll see that the streamline are no longer straightforward. So they are going to be turbulent. So this is happening actually somewhere here. The angle of this is increasing, and see that the wake is happening here, or the flow is going to be turbulent. So another classification of the, as we said, we have a steady flow or unsteady flow. A steady flow is once the streamline are time independent. For unsteady flow, once you have time dependent. So in this flapping wing drone, or in this like a hummingbird, as we can see, once it's flap, the flow is totally different. So the flow is also, these characteristics are changing based on the frequency of the flapping motion. So here we are dealing with the unsteady flow. So the classification can be based on a Mach number, subsonic, transonic, supersonic, and hypersonic. It can be based on the laminar or turbulent, as we showed in these two pictures, based on the Reynolds number, and based on the time, which can be a steady. As you can see, this is a steady flow, and this is going to be an unsteady flow. This is just some basic actually information about aerodynamics. So any airfoil, once is exposed to the flow, it would generate the lift and the drag force. So the lift is a normal force, is generated by actually the flow once it's passing through your object, once it's moving in the air, because of the pressure difference. And the drag is happening because of the friction that the flow has with the surface of our wing. So what I wanted to mention here is that these are some fundamental that how lift and drag can be calculated. So here, this is actually the out of scope of this course, but since this is just general information and the fundamental of the aerodynamic, maybe some of you guys, you are interested to have this material. So I am going to actually, I have included them in this lecture. I'm not going to ask you about this material at all, but just for your information that how much is fundamental behind the aerodynamic analysis. So this is the fundamental that how we can measure the lift and the drag or the momentum once the flow is passing over an airfoil. So here we talked about this slide in our previous lecture, that we actually see something we proved. Once the flow is passing through an airfoil, we have higher velocity at the upper side and the bottom side, and therefore we have the lower pressure at the upper side and the bottom side, so it will create the lift force. So this is the way that the lift is created. Once your airfoil has an angle of attack, this normal force, it has a component of the drag as well. So the drag, so if this airfoil is or wing is moving in this direction, so here in the negative opposite direction we have the drag force, and we talked about this earlier, that how the lift and the drag can be calculated based on the characteristics of your wing. I will show you through the software with more detail later on. So these are the other fundamental for calculating momentum coefficient and other aerodynamic coefficient. This is called Buckingham Pi theorem, that is based on the units. So as I said, this is going to be out of scope of this course, but what I want to show you here is three factor which shows the type of the flow. So which one of them, RE, is stand for the Reynolds number. This is the Reynolds number that we discussed, that how the Reynolds number can be calculated. The M is Mach number, and alpha is angle of attack. So once you have any type of aerial system, once it's moving in the air, these are three conditions that determine the regime of the flow. So the first one is the Reynolds number that we discussed about that. And we said that Reynolds number is going to be equal to the density times free stream velocity of the flow or your object times c, which is a chord length. We talked about the chord length divided by dynamic viscosity. The Mach number is defined as v, velocity here, divided by c, which is the speed of the sound. So these are some actually parameters, and they are non-dimensionalized, and they don't have any dimensional units. So here, these are actually determining our lift coefficient, drag coefficient, and momentum coefficient. So this was a part of the lecture for today. I just wanted to give you some information for this material. So the other lecture that we'll talk today, and this is going to be more our system design, is actually for sizing process of any type of the UAVs or aircraft, that how we are going to do the sizing process. So the material that I am discussing here, we will see that how we can design an unmanned system or an aircraft based on the preliminary design or conceptual design. So we talked about conceptual design and the preliminary design. So now I'm going to show you a step-by-step of design process of unmanned system or manned system. So before designing any type of the aerial system, we need to run the sizing process. Sizing process means that what should be the limitation on the weight, the limitation on the dimension, the limitation on the flight time or endurance, or the flight range. So there are some constraints that we need to consider then once we want to do any design for our aerial system. So the sizing process is the first step that we need to do before moving to other steps, for the design process of any aerial object. So the first step that we need to do is mission analysis, that we need to know why we are designing our drone or aircraft, what is the mission is supposed to do, and what should be its flight range, what should be the flight time, what are the limitations on the weight or size, so what are our flight pattern, what is the flight routes. So these are some components that we need to consider once we are doing our mission analysis. So for example, if I fly a drone on Mars, the design is going to be different with flying this drone on Earth, because the atmospheric conditions are totally different, and the type of the mission eventually would be affected by the environment. So in the mission analysis, beside the different components that we are determining, we need to also know about the climatic conditions. So the climatic condition is, for example, the wind speed, is the temperature, pressure, the viscosity or density of the flow or atmosphere that our aerial object is supposed to fly on that. So this is, a part that we need to do more investigation, as I'll discuss this in more detail. And then we need to know what speed our airplane or our drone should have. We need to know our flight mode. There are a variety of flight modes that we'll discuss this later. We need to determine the shape of our wing. Are we going to select a bird-shaped platform, or we want to have a Zimmerman, inverse Zimmerman rectangular wing shape, delta shape, or tapered wing shape, sweep back. So there were varieties of the wing shapes that we actually discussed about them in our previous lectures. And we need to determine the aspect ratio. So if you remember, aspect ratio was wingspan square divided by wing area. So we also need to do the constraint analysis. So this is one of the fundamental part of this work. Again, I'm going to skip to talk more detail or mathematics in this part, but I'll just show you overall view and show you the physics behind this constraint analysis and what idea or what we are going to get from running this type of simulations. So there are, in the planform aspect ratio, we have aspect ratio and we have the shape of our wing. In the constraint analysis, it's based on the mission, the flight mission that our drone is supposed to do, and our aspect ratio and our speed or mission characteristics. So based on this, we run the analysis which is called constraint analysis. So the output of constraint analysis are two factors which have important role in the design process or sizing process of our drone or aerial object. So one of them is thrust loading, the another one is wing loading. So T stands for thrust and V stands for the weight or total weight of our airplane. Wing loading is the ratio of the total weight of our aerial object divided by surface area of the wing. So if you have a drone or fixing UAV or UAS, so if you measure the weight of this drone divided by surface area of the wing, we will get the wing loading. And this is actually two main factors that we need to consider them in the sizing process. Then we need to do the weight estimation. So we know that what mission our airplane is supposed to do, what sensors are going to be carried out by our drone, or for example, what time we need, how long flight we need, and what flight range we need. So based on that, we can specify some of the electronic components. So after specifying electronics components, we can estimate the weight of our structure, and eventually we can do the weight estimation. So we can estimate the weight of our airplane. So from this stage that I want to show you, if we estimate the weight of our airplane, we have W over S from constraint analysis. So from having weight and W over S, so the only unknown here is S. So here I have the W, I have the ratio of W over S, so I can find S, which is my wing area. So I have the value of the aspect ratio because I have determined that based on the, again, flight mission. And I found my S here. So I have AR, which stands for aspect ratio. We have my wing area, so I can easily find the B square, and I can take the square root, and I'll find the B, which is the wing span. I have the wing span of my wing. I have the shape of my wing. Eventually, I can find the dimension of my wing. So I have the dimensions of the wing. So I have the length characteristics, which is called mean aerodynamic chord, that I showed you how to calculate it. I have the density and viscosity and the flow velocity of my airplane. Then after this, I can easily calculate the Reynolds number. So just to show you again, the Reynolds number was rho times velocity times C times viscosity. So from climatic conditions, we can have rho and mu, right? Because these are the atmospheric characteristics of the region or the area or environment that our aerial object is supposed to fly. So we have velocity here. This is given during the design process. We need to know what is speed our airplane should have. So we have rho, we have V, and we have the mu. The only parameters that we are getting from him is C, which is the wing characteristics length, which is the chord length. So this chord is mean aerodynamic chord, which I showed you earlier. If you put here, you'll find the Reynolds number here. And this Reynolds number actually is going to show us what regime of the flow we are dealing with. Are we in the laminar flow or we are in the turbulent flow? So now this was the sizing process. So now I'm going to talk about one by one of this process that we had here. So the first is start with the mission analysis. So as I said, in the mission analysis, first of all, we need to know, are we going to fly our aerial object or drone in the indoor space or outer space? Outer space means you are in the free air, in outside. In indoor space, so for example, if I fly my drone in an environment like this room, or for example, in the classrooms, in the buildings. So here I am dealing with the indoor space. So imagine that, for example, earthquake happened and you want to send the drones for search and rescue. So these drones that you are sending should be able to work in this confined space. So why this is important? Why we need to consider indoor or outdoor space once we do the mission analysis? So the main thing here is that in the outdoor, we have change in temperature, because depending on the time or hours in the day, so the temperature, because of the sun, is moving, and the amount of the radiation that the atmosphere is receiving, the temperature is changing. So we know there is a big change in the temperature during winter or summer, or at the early morning or evening or at the noon. So here, since the temperature is changing, temperature would affect on the atmosphere or air density and the viscosity, because density and viscosity of the air, they are changing with the change of the temperature. So then we have the wind speed, right? So we have a speed of the wind that we need to consider them once we want to design our aerial object. But once we go to the indoor space, for example, inside of the building, the temperature is almost constant. So it can be 25 degrees or 20 degrees, depending on, the type of the building. So the temperature is almost constant. So the second factor is that we don't have any wind speed. You may turn on the cooler, but imagine it's off, right? So, or it's not changing randomly, it's a constant. So this is a difference that we need to run the analysis once we do the mission, defining mission, that where we are going to fly our drone. So these are some examples of the outdoor missions that, as we can see here. So once you have the mission, the next step, we need to select the configuration of our drone. So for example, if we fly our drone in the indoor space, we cannot have a fixed wing UAV because they have the higher speed and they cannot fly in indoor space. Because of this, we need to consider flying our drone in, for example, which has a configuration of the flapping wing or a multi-rotor, which can do a hovering flight, which can stay in the air or in that environment. So we need to design the airplane type. For example, if you are dealing with the fixed wing, rotary wing, tilt rotor, tilt wing, vertical takeoff landing, or flapping wing, or multi-rotors, there are varieties of configuration of drones that we talked earlier about them. So based on the environment that they're flying, we can select the appropriate concept or configuration for our drone. Then we have some size limitation. So for example, I'm not able to make a flapping wing with, let's say, 2 meter wingspan, because you don't have any bird with those size that which they flap, right? Or 4 meter wingspan or 10 meter, but you can make an airplane with a 10 meter wingspan or 20 meter wingspan. So we have a size limitation. We have a limitation in the size, we have a limitation in the weight, we have the limitation of the time. So for example, if I have a flapping wing like this that we saw it earlier, so I have the limitation of the flight time that this flapping wing can give me. I cannot fly this flapping wing, for example, for more than 20 minutes. So this is so important, that how we actually consider this limitation in the time, weight, or dimension. So after selecting the environment, the type of airplanes, and having this constraint, we need to do the mission analysis. Mission analysis is composed of 2 parts. So the first part is preparing the flight plan. So what is a flight plan? And the second one is determining the flight modes. The flight plan, it means that how long flight time we need, what should be the endurance, what is the flight range? Is it going to be fly for 100 feet, 100 miles, I mean, what is the distance that our drone or airplane is supposed to fly? So for example, if you look at this example, this is an outdoor mission. The radius of the flight range is around 60 kilometers. The flight altitude is 10,000 feet, and the speed is 120 kilometers. So it shows you that how this airplane can start from here and do a mission and then get back to here. So if we compare this with the indoor space, everything will be totally different. So here we need to consider, depend on the configuration that we are selecting or the limitation that we have for airplane type. So we can select actually our flight time. So for example, I'll say that I want to design an airplane which fly for 20 minutes. Or for example, I want to design something that fly for 100 miles. And then we need to also determine our atmospheric conditions. So for example, as I said, if you design a drone for Mars, the design would be totally different with the drone which is flying on Earth. Or for example, if you fly your aircraft in Arizona, Phoenix, the efficiency of your flight is going to be different with the flight that you are doing in Alaska, because it's in the summer, it's so hot in Arizona, but in Alaska it's cold. So here, this temperature difference would change the density of the air. We have different speed of the winds. We have different level of the radiation. So because of this change, we need to determine all of them once we want to do the design or sizing process of our airplane. So there are different varieties of flight modes that we discuss later on in this lecture. So for example, if you want to make an airplane which can do the hovering like helicopter, so the design would be different with the fixed-wing UAVs, which just have a front rotor, or propeller, which is just generate the horizontal thrust. Or if you want to have a combination of that, you can combine, let's say, rotary wings with the fixed wing, and then eventually you can have a tilt concept. You can have tilt body, tilt wing, or tilt rotor drones or airplane. So this is an example of the outdoor and indoor space. So as we can see here, the flight zone can be indoor vs outdoor. So here, this is one example of the mission and how we extracted the lengths that the airplane is supposed to fly, the turning radius. So what are these missions that our airplane is supposed to do for outdoor space? And this is an example for indoor space. So these are two examples that I actually made some drones based on this feature for an international competition. So here in this outdoor, the drone was supposed to take off automatically here, go in this direction and turn here with a radius of 8.5 meters, go into the forest. There is a truck here and something is written at the top of the truck. It should actually take a picture, run image processing. There are two balloons in the sky, so our drone should be able to attack to these balloons. There are two arc shape here that our drone should pass through this arc and need to drop a sensor in this flight zone or drop zone and eventually land it here. So this is an example of the mission that we actually did for outdoor application. This is an indoor mission, as we can see here. So here I cannot design a fixed wing drones to do this in the indoor space. So this should be a flapping wing or a multi-rotor, which should be take off here. Going to this window to the building, and there are some columns should pass through them. It should be able to drop some sensor here and then eventually land in this point, or maybe grab this component and then land here. So this is one of the example of the indoor mission. So once you are designing a drone, or unmanned aerial system should be able to follow up what we are asking for. And this is another example of the flight routes of an airplane for agriculture application. So as you can see here, it's so complicated mission. So, but actually you can simplify this, say that it should pass through this, and then you can decide what flight plan do you want to have? And this is another example of the airplane for outdoor mission. So again, if you want to summarize what we discussed, we need to know our flight zone, we need to know our flight pattern, we need to know our flight distance, flight time, and flight modes. So for example, if our airplane fly, we should have different flight scenarios. So for example, it can be takeoff or launch or hand launch. If we have a big airplane which has a landing gear, so they are going to take off automatically from the runway. If we have a smaller drone like this flapping wing, this should be able to hand launch, right? So we are going to hand launch it. Or we can have climbing, so airplane should climb to a certain altitude. Then we have a cruise flight, which usually 80% of our flight time is cruise flight. Then we have the loitering or turning, so it should turn our airplane. We have descending and eventually landing. So we talked about flight zone, we talked about flight pattern, flight distance and flight time. These are something required in order to initiate the design. And then we have the flight modes that we'll discuss later on, which, as we said, that flight modes, we have different scenarios for flight modes. So these are the flight scenarios that the airplane is takeoff here. This can be takeoff, then climbing. So this is climbing and then going to cruise, then loitering in case if it need to turn on and go back to the same runway. Then we have descending and we have the landing. The same is happening here, different segments of the flight to reach to a certain altitude. So here it shows that how the landing is happening, then climbing is happening, then you have a cruise flight, you can have an accelerated flight. So these are different components or different flight phase that we need to consider them once you are designing our airplane. So we need to know what is the speed, how long distance, how long should flight, what should be the time to take off, what should be the time to climbing, how long or what distances our drone should be in the cruise flight, or the other phases of the flight that we have. So these are different types of the flight modes that's happening in the aircraft that I want to show you. The flight modes can be have a forward flight, it can be hovering, it can be gliding, it can be soaring, dynamic, thermal, and slope, and it can be bounding, which is happening mainly in the birds and the flapping wing. So the forward flight is like this glider. Once it's flying, so it's just flying forward, or like this aircraft, as you can see here, this firefighter. We can have a hovering like these helicopters is actually doing the hovering. We can have a gliding, again, like this glider. So this gliding is using gravity acceleration to glide, and actually is actually somewhat forward flight. We can have a soaring and a bounding, which mainly happens on the birds that he'll show you in other slides. So once we determine the flight modes, in each flight phase, we need to know what modes we want. So for example, if you are doing a takeoff, right? If you're doing a takeoff or landing or cruise or turning or loitering, climbing and descending, each one of these flight phases can be done by different flight modes. So for example, in the takeoff, depending on the type, you can have a landing gear, you can take off as a forward flight. If your concept is a VTOL, vertical takeoff landing, like this helicopter that we don't need runway, they can do the hover flight. So they can do the hovering. Or for cruise, you can have the transition for forward flight, for the turning, climbing, and descending, or airplane can do the forward flight or hovering flight. So we can have a different flight modes for each flight phases that we have here. So this is different flight modes that the birds are applying. So the first one is the forward flight, just simple flapping wing that you can see here in this pigeon which is flying. You can see the hovering, that's this hummingbird or this actually pigeon, they are doing hovering. Usually smaller birds or insects, they can hover a longer time than the bigger birds. So these birds, they cannot hover for a long time, but these hummingbirds, I mean, all of their flights is hovering. We also have the gliding. This is a gliding. As you can see, this eagle is harvesting energy from the gravity acceleration in order to glide. We have three types of the soaring that I showed in this picture, just two of them, including thermal soaring. Because of the temperature difference in different layers of the air, we have upward lift, which the birds usually can take advantage of this, and they can go up without flapping motion. And this is a dynamic soaring, which usually happen in the migratory birds like albatrosses, that they are harvesting energy from the shear wind over the waters, and without flapping motion, with just changing the banking angle, they can fly in this trajectory. We also have the bonding flight, which the bonding flight is happening in the small birds. In order to save energy, they usually flap, and then they fold their wings, they open their wing and flap again. And due to this, their flight motion is in a sine wave. So they are going in the sine trajectory. So these are the different flight modes that we have. So again, after determining the flight modes, we need to know our flight distance, flight time. So these are the given. So for example, if you know our drone is supposed to fly for 200 miles in 2 hours, so we can easily get our cruise speed. Since, as we said, 80% of our flight is a cruise flight, so here we can determine or estimate the speed based on this given criteria, including the flight distance and the flight time. So we also need to determine our atmospheric condition, including the latitude, the sailing, the wind speed, the gravity, the pressure, temperature, viscosity, the density of the flow. So these are the different components that they are all related to the flight environment where we are going to perform a flight. So as I said, if you fly in Arizona, we need to consider what latitude is that, and what type of gravity we have there, what is the pressure, temperature, viscosity, and density of the flow there, what is the wind speed, the range of the wind speed there, and in what altitude our airplane is supposed to fly. So once you have all of those criteria, we can actually, through these equations, we can find out these values. So, or we can actually, after calculating this rho and viscosity and all of those, we can easily calculate the Reynolds number and Mach number. As I said, once you have the speed of the flow, we can easily estimate our Mach number. Once you have our Reynolds, given, we can easily find the regime of the flow, that if you are dealing with the laminar flow or the turbulent flow. So these are some equations which shows you that how with the changing the altitudes or elevation, the temperature is changing, or how the density is changing, how the kinematic viscosity is changing, or how the density is changing based on this pressure or temperature that we are measuring here. So I'm not going to ask you at all about this equation. There is a software which is called Aximer. If you want to download it, it's free to download. I think I should have it in my computer, and I may be able to show you how to find this software. So this is going to be a software, is called Aximer. If you go to the Google and say search for Aximer software for aerodynamics or atmospheric characteristics. So this is the MS Aximer free aerospace engineering software. You will go here, and this is download MS Aximer aerospace software. You can easily download the software. It says it works for Windows XP and Windows Vista. I want to try that, if this is also applicable. It seems that this is not This is a RAR file that if I extract it here, see that how this works. So it seems that okay, so you can easily install the software. So let's see how this works, and hopefully it works for the Windows 10, because I know this is an old software that we were using for analyzing the different parameters. It seems that, okay. So this is not compatible with Windows XP. Okay, so if you have, I mean, the old version of this software, you can easily install it, and we will be able to actually use this software to measure the atmospheric characteristics. So I have an example here. For example, if you put the altitude, so the altitudes, so you can, gives you that, for example, what is the value for gravity acceleration, the pressure, density, and the temperature. So the software that I'm going to teach you, XFLR5, actually has this capability that, I mean, we may not need this software, and XFLR5 can do this type of calculation for us. So just to show you why these parameters are important, I'm going to show you one of the research works that I have done during my PhD, and this shows that atmospheric characteristics of different solar bodies. So for example, in the Venus, Earth, Mars, Titan, and Uranus, this shows that how with changing altitude, the temperature, pressure, viscosity, and the density of the air is changing. So some for, I mean, planetary exploration, as we discussed earlier, we need to design some drones which are able to fly in those conditions, specifically space drones. So this type of aerial objects, since they are flying in a different environment than Earth, so we will have different scenarios. So for example, because density, viscosity, temperature, pressure, which are all factors we discussed here, and including the gravity, they are all changing on Mars or on Venus. So for example, if you remember at the first lecture, we talked about this, that Venus has a harsh condition, so these characteristics are different. So we need to have a good idea about these atmospheric characteristics if you want to design a drone which is supposed to fly there. So these are some analyses that we have done here. We need to know, I mean, the environment that our aerial object is flying. There are 7 or 6 type of the speed that they are important once you want to do a design. The first one is cruise speed. This is defined as the speed of your aerial vehicle that is maintained in cruise phase. We have the stall speed. The stall speed is actually the slowest speed that your airplane or your flying vehicle, it can fly to maintain level flight. If you fly with the speed less than the stall speed, the stall happens. Your airplane would crash. So why the stall is happening? There are 2 main reasons once the stall is happening. The main reason can be increasing the angle of the attack of your wing and separation of the flow. The flow is no longer attached to your wing. As you can see here, this airplane which is flying, the angle of the airplane is increasing, and you see that there is some wake is happening here. And because of this, your airplane, the speed should be decreased, and this way your airplane cannot generate enough lift, so it would crash eventually. We have the loitering speed is a speed that in the phase of the loitering. So if your airplane wants to turn, so this is called loitering flight, and usually the speed of the airplane in the loitering is about 60% of the cruise speed. So if I define the loitering speed with the VL and the cruise speed with the VC and the stall speed with the VS, so the VL, which is the loitering speed, is usually 60% of your cruise speed. So the takeoff speed, climbing speed is also something important, and the launch speed is specifically for the drones. So if you have a drone and we need to launch it with a specified speed, that how we are going to calculate that for fixed wing, micro aerial vehicle, or micro unmanned aerial vehicle, your launching speed, your hand launch, should be almost equal to 1.2 of your stall speed. So 1.2 of the stall speed. So this is one of the important speeds that we have, and we usually need to determine them before designing airplanes. So for example, you will say that I want to design an airplane which is flying with 20 meters per second, and it should stall speed or minimum speed 6 meters per second, and I need to do the hand launching, right? So the hand launching is going to be 1.2 times 6, which is going to be 7.2 meters per second. So I need to do this. Or for example, my airplane should be able to fly with the 12 meters per second for the loitering flight. So these are different speeds that they are always given as for the sizing process. So we talked about wing shape and the planform and aspect ratio in our previous lecture. We talked about flight modes and atmospheric characteristics, and also climatic condition and the flight mission. So there are two more steps that in today and next lecture I'll talk about a little bit fundamental behind that. So as I said, I'm not going to show all of this equation and ask you about this at all, just to show you what is the physics behind this and why this is happening, why you are doing this calculation, and how we can select our wing loading or thrust loading. So now if you look at this airplane, we said that there are four main loads or forces that are acting in any type of aerial object, including the lift, which should compensate the weight, and thrust, which should compensate the drag. So these two equations that we have here, and again, I'm not going to ask you, and you don't need to know about them more details, is that if we write the second law of Newton, thrust minus drag, lift minus weight, is going to be equal to, so the second law of Newton was F equal to mass times acceleration. So if I have, these are my force. If I have my forces equal to mass, weight divided by gravity acceleration gives you the mass, time the horizontal and parallel or perpendicular to the velocity or horizontal or vertical acceleration. So after doing this, what I want to show you for any type of airplane with the angle of attack, this is a general equation for constant analysis. So thrust loading versus the wing loading. W over S was wing loading, T over W was wing loading, was thrust loading. So K1 is a constant, N is constant value, beta is constant, Q is the dynamic pressure, is 1/2 times density times velocity square. Here again we have S over W, which I can write the W over S in the denominator. CD naught, CDR are all constant, and PS over V is based on the flight scenarios. So if we have, for example, if our airplane is supposed to fly in constant altitude or constant speed, or if we're flying a constant speed climb, it's climbing with a constant speed. Or for example, constant altitude and the turn, speed turn. Or for example, horizontal acceleration, our aerial vehicle is accelerating horizontally, or doing the takeoff or landing or hand launch. So these are the different scenarios that we talked about them already: loitering, cruise speed, takeoff, landing, hand launch, right? So this general equation that I showed you here, again, I'm not going to ask you or expect you to know about this. This general equation can be simulated for each one of these flight scenarios. So for example, if you have cruise flight, your flight is going to be different with climbing, right? So you have a different scenario. So this equation would be simulated, and eventually what we will get is like this graph. So what does this graph means? So the equation for constant analysis, if I want to simplify that, it was thrust loading as a function of wing loading. Right? Thrust loading was as a function of wing loading. And we had different scenarios: constant altitude with the cruise speed, constant altitude turning or loitering, climbing with the acceleration, climbing or descending with the acceleration, or landing or takeoff or hand launch. So each one of these scenario, there is a different equation for thrust loading once you're writing based on wing loading. So now if I consider range for my wing loading, I will have the value for thrust loading. So this graph, it shows you that for different flight scenario, how this thrust loading is changing based on the wing loading. So for example, this dashed black line is constant speed climb. It shows this. Or accelerated climb is this, or for horizontal acceleration is this. For constant altitude or turning is this blue one. And eventually we have for takeoff or hand launch, which is going to be this one. So once we are looking for a design space, or solution space. So we need to pick a point here in this area which would satisfy our thrust loading. It means that our airplane or our propulsion system that we will design out of this can generate enough thrust to perform all of these flight scenarios. And also, we need to minimize our size of drones as much as possible to reduce the drag. So what would happen here, if these are different flight scenarios, we need to select the wing loading, which is W over S, as maximum as possible. So this is the reason that this should be close to this constraint, that vertical constraint, which is for takeoff, as much as possible. So once we want to select the wing loading, so we should move in this direction and select a point which can satisfy actually this. I cannot select a point here, and this is going to be wrong, but I can select a point here. So in an optimum way, so this point should be moved as maximum as possible. Why? Because we want to increase the payload capability of our drone. We want to increase the weight as much as possible for a constant amount of the surface. So once I'm increasing the wing loading, means that I'm increasing the weight for a specified surface area. So it means that I'm increasing the payload capability of my airplane. And also, I need to select a point somewhere that it would satisfy all of this flight scenario. I cannot select my point here because it cannot, my thrust loading is going to be less than this point, which I need for, let's say, constant speed climb. So it should be satisfy all of those. So I can select a point here, but this is not optimized because it's more than what I need. So therefore, you need to select a point which is actually close to these lines. So this is called design space. So if I want to mention it here, we are selecting actually the points that they are, they can give us the maximum possible wing loading and minimum possible thrust loading where satisfied is. So for example, I can select a point here. So what I'm getting from here, so for example, I'll get my wing loading, W over S is equal to 55 Newton per meter square. So if I then in the next step that I'll teach in the next lecture, if I estimate the weight of my airplane, so with having this value, I can easily, and having the weight, I can easily find the surface area of my wing. I had the aspect ratio value, which was wingspan squared divided by surface area. I had this aspect ratio value. I found my S from here. So if I find here, I can easily find my P. This is something exactly I showed you in the flow chart. So thank you so much for your attention in this lecture. If you have any question, again, please feel free to contact me. I just wanted to show you some fundamental behind the aircraft design and sizing process. Again, I'm not going to ask you at all about this material. I'm not going to expect you to know this material or this equation. It's just for information that you may need. I'm going to submit this file on Canvas to just show you something on Canvas, that how you can visit the lectures. So if you go to the Canvas here in all course, you will find summer 2020, or I mean, if you're watching this for the fall semester or spring semester, you should be able to see your section. So here I have put the syllabus, of course, some pre-tests that you need to take it, introduction to structure and to research lab that I have here. And these are the lectures video that I am uploading here. So you may have some problem in opening some of this file. I'll just show you how you can open it here. So for example, if you go to lecture 5, you need to click here in lecture 5 video, and it will take you to the video that this lecture has been recorded. Or for example, if I go back, I am going also uploading the lecture. So if you go to lecture 5, you will also get to the lecture here. So you shouldn't have any problem in opening this file. So this is, for example, one of the previous lectures that I have uploaded. So again, for any lecture that you go here, you should just click here at the upper side and will open the PowerPoints or the lecture. So you will be able to download them, and please feel free to ask me any question that you have. You can reach me with this email that I have here, and I am looking forward to the next lecture. Thank you for your attention again.